Good day, everyone. Today is January 31st, 2019, and this is a live webinar. My name is Mike Lesiecki, and I'm your host. Today our topic is neural interfaces, the nanoscience and materials technology involved with these unique materials. We'll hear a lot about applications today as well. This webinar is being recorded, and you'll automatically receive a link to the recording. Let me acknowledge our hosts for this webinar, ATE Central. ATE Central is the information hub for the ATE community. You can find out more about them and all the resources they offer at atecentral.net. Our sponsors today are the NAC Network at Penn State University, the National Coordinated Infrastructure Southwest at Arizona State University, and the financial sponsorship of the National Science Foundation. This is a good time to mention that the opinions expressed by your presenters today are theirs alone and do not necessarily reflect the views or opinions of the National Science Foundation. Thank you. Let me make some introductions. It's me, Mike Lesiecki, on the left. I'm your moderator and host for today's webinar. And also joining us is Bob Ehrmann, the Managing Director of the NAC Network. Bob is located at Penn State University, which is actually closed today, as many institutions are in the United States Northeast and Midwest parts of our country due to severe weather. Bob is having what they call here a snow day. But Bob will be joining us by the chat window, so let's look forward to his comments there. Also joining us is Ozgur Cakmak, Assistant Professor at Penn State University. He's been an important part of the NAC network for a number of years and recently became Assistant Professor at Penn State. Ozgur, thank you very much for joining us today. Would you come on for just a moment and say hello to the audience?
Hello, everyone. My name is Ozgur, as Mike said. Yes.
Good. Your audio level sounds very good. Ozgur, thank you for joining us. Now let me go ahead and continue our introductions of our speaker today. Joining us is Steve Sadow. Dr. Sadow's research interests are to develop a wide bandgap semiconductor materials for biomedical applications, MEMS applications, and nano-MEMS applications. His research group has worked extensively with unique compounds like the silicon carbides he'll be discussing today. Steve was recently appointed to the Department of Molecular Pharmacology and Physiology in the College of Medicine at University of South Florida. Steve, your work is very interdisciplinary, but did you ever imagine from your engineering background that you were going to be working in the College of Medicine?
Hello, everyone, and thank you, Mike. No, I never did. It's in some ways a dream come true, so I'm looking forward to talking a little bit about what I'm doing in that area and how I got here today with you all.
Excellent, Steve. We're going to now turn the webinar over to you. I'm going to advance to your first slide, and then you just take it from there.
Thank you, Mike. Well, hello, everyone, and as Mike mentioned, hope you're having a good day without too many polar vortex challenges wherever you are in the world. So just a quick outline of what I'm hoping to accomplish. I'd like to start with the healthcare challenge, why neural implants are so important, and why interdisciplinary science and engineering is required to make them useful devices to help people who are suffering from a whole range of diseases and maladies and also brain damage. I'd like to talk a little bit about silicon carbide biotechnology. Silicon carbide is a semiconductor similar to silicon in our computer chips. It's mostly known for high power electrical power supplies and switching, electric vehicles, and so on. But there's a niche here in the biomedical realm that we've been exploring for more than a decade, and I'm really excited to talk to you about that today. Getting into a little bit of the details of that, we'll show some of the results of in vitro studies, some of the biochemistry, the nanoscale phenomenon involved with bedding any type of material for the body for use in humans. Some results in the area of silicon carbide biosensors, mainly to detect glucose and hemoglobin. Again, with the nano flavor, so I want to include that. A little bit about brain-machine interfaces, or BMI, which is the main let's say, umbrella of technologies behind therapies such as exoskeletons, bionics, neuroprosthetics, and so on. And finally, a little bit about how silicon carbide works in the body. And I'd like to close with a discussion about the opportunities and challenges that we face as educators in preparing the next generation workforce. So let's go ahead and get started. And please, any questions, chime in, I suppose, in the chat window. And Mike will save all of you from my over-enthusiasm if needed. So please chime in as you need. So first of all, what are neural implants? This is maybe something that you've heard about, Iron Man and a lot of science fiction and television shows nowadays talk about this. Can be used for multiple organs in the body, everything from the brain to the colon, from the head to the other end of our bodies. We use them for recording signals, biophysical signals in the body, and also for stimulation to reanimate motion or help reduce tremors in Parkinson's patients, or to actually obviate the need to use opioids and other painkillers to deal with pain, which is kind of a nice thing. So here's an example from DARPA of a program talking about electroceuticals, and gives you a little bit of a very high altitude overview of the technology, but we're talking about the nervous system, which of course runs throughout our body, peripheral and central nervous system being our brain, organs, monitoring our health status, and of course we want to be able to monitor, record, and treat various conditions in the body. So neural implants are important for that. One example that I like to show, this is from 2012, this woman had suffered a car accident, hadn't been able to walk for 5 years. And using an exoskeleton, she was able to walk on her own again, which is fantastic. The downside is that she has to use these two sticks to control her orientation, and behind her is actually a technician with a remote control helping to make sure she doesn't topple over. Clearly this is not a transparent, seamless assistive device for her. We'd like to be able to get rid of this exoskeleton and have some way to reanimate motion in a more natural way. Another technology, EEG, where we use brain waves recorded on the scalp or above the scalp, allows us to do a lot of things. Very useful in psychology, but as you can see here, it's not exactly a very comfortable technology to reanimate motion. If you lose a limb or you're not able to communicate with the computer and you're immobilized in a wheelchair, this could be one approach. We'd like to find some other means, again, to more seamlessly assist people who are suffering from neurological conditions. So finally, we get to what's called the Decca Arm, which was developed and sponsored by, or developed through funding from DARPA, and it's a very advanced 22-degree freedom motion arm. But as you can see from this image, this woman who lost her entire left arm, the interface to the body is through muscle motion in both her shoulder blade area in her back and also on her chest. So clearly very cumbersome, not very comfortable, and we'd like to be able to remove all the bulky things and directly plug into her nervous system, because the commands from her brain to control her hand and her arm and so on are still being sent from her brain down her spinal cord to where her arm used to be. If we can intercept those signals and we can seamlessly route them to the robotic arm, then we would basically have, if you will, the Luke Skywalker hand from the famous Star Wars movie. So what's the motivation here in a nutshell? We're looking at neurostimulation for the peripheral nervous system, which again is used in pain medication, has been shown to actually assist patients in being able to walk again, to overcome spinal cord injury, neural connections in the brain, which it can help with speech, and obviously with hearing, the cochlear implant's a good example of such a device. And then we can also boost neuroplasticity, and what that means is our brain's ability to reroute neural connections around an injury site. We can actually enhance that through neuromodulation. So there's a lot that we can do here. I'd like to turn over to Mike now to a YouTube video that shows an example of a Parkinson's patient being treated with EB. So go ahead, Mike.
Thank you, Steve. Now, colleagues, let me just take a moment and talk about how this video will play. It's short, just a little over a minute long. But when I launch the video, for many of you, it will appear in a new browser. So once the video is complete, just turn it off and come back to this browser. For our presenters, Steve and others, please don't stop the video because you'll stop it for everyone if by accident. Some computers, some older Macintoshes won't play the video. We'll provide the link to you later. So let's go ahead and launch this. Again, it'll take just a minute, and let's see what it has to say. Just a moment here. Okay, I'm launching now. Well, thanks, everyone. Steve, we're back live now from the video. Again, I'm not sure that played for everyone, but I'll make sure I put the link to it in the chat window. So you could go ahead.
That'd be great, Mike. So as everyone who could see the video, I still get emotional when I see this. To see someone who is really unable to live a quality of life, to be able to then have control over his body or her body through the use of deep brain stimulation using invasive neural implants. I mean, to me, it's nothing short of miraculous. Drugs can't do it. This has to be done using an engineering solution, which, of course, I'm very proud to give it as an example. It's just one of many examples. We can treat depression. We can treat, obviously, other phenomenon, loss of a limb and so on. So there's a lot that we can do here. So, what are some of the challenges? I want to talk about that in a little bit. But let's talk a little bit about what the technology has to offer. And this shows an example, this next slide, of some severe tissue death. This is a superimposed image of electrodes, DBS electrodes, where they had been placed in the brain. This is tissue histology. So after the patient had passed away, they sectioned his brain or her brain and looked to see what had happened. And you can see where the bright purple and pink colored areas are, and where the black area is, quite literally, is where brain tissue has been lost. So what would happen initially is the probes are put into the brain. The clinician will start to do a regimen of electrostimulation, perhaps at a volt, to give you an idea roughly of the number. Of course, it depends on the power and the current. But let's say they start out at about a volt, and they're able to get neuromodulation that's effective. Over time, due to the interaction of the probe materials with the brain's immune response, fibrous tissue, what's called a glial scar, begins to build. The way to overcome that, let's just increase the juice. We increase the potential. You still get the treatment to work, but eventually it will stop functioning over a longer period of time. And so our goal is to replace, in this case, tungsten metal wire electrodes coated with parylene C, which is a quite nice biocompatible, neurocompatible polymer, replace that with a much more durable material. Silicon carbide, by the way, is a ceramic. The stuff is extremely corrosion resistant and resistant to the harsh environment of the body, and that's what I want to leave with you today. So the idea is that we would like to be able to take some of the great work that's been done in the last 40 or 50 years at the University of Utah, University of Michigan, involving silicon, microelectrode, MEMS type arrays, and see if we can't pretty much take the same architecture, same strategy, but replace silicon with silicon carbide, get rid of the metals, get rid of the polymers. Polymers tend to degrade over time, and just use an all silicon carbide approach. And we actually demonstrated the beginning of that idea, which is quite fantastic. So the challenge is to try to find materials that will survive in the body and function for at least a quarter of a century, because of course we want to have these implants put into the brain of the patient and have them there for the rest of their life. So why semiconductors? And maybe this audience is quite familiar with semiconductors, maybe not. So let's talk a little bit about material science 101. We have basically polymers, plastics, we have metals, and we have, for conductors, and we have semiconductors. And the idea is that polymers are normally electrically insulating. There are some conductive polymers. They are not always terribly compatible with the body, but there are some like PDOT that do work well. But again, polymers are inherently biodegradable. They're used for time-release capsules, great materials, but not terribly robust in vivo. Metals are also fantastic materials. They're hard, strong, and durable, but they do tend to corrode, shed particles. They're chemically reactive inside the body. And in fact, most of the metal electrodes that are being used have been treated so that the actual surface of the metal is more of a ceramic. Alumina being the ceramic version of aluminum, iridium oxide for iridium, and so on. So the idea is that you will take a metal, form a very thin ceramic surface to make it more robust and to last longer in electrochemical environments like the brain. Now, semiconductors are, as we know, fantastic materials. We can do complex electronics. We can realize sensors. We can do drug deliveries with things like microfluidic chips. We can clearly do diagnostics. But of course, the question is it biocompatible? Is it hemocompatible? And for most applications, we need both, especially for the brain. The brain blood vasculature is extremely dense. It's basically a huge radiator in the brain. And it's pretty hard to implant anything in the brain without subtending a blood vessel. The moment you do that, if you're not hemocompatible, you definitely have a problem with the interaction of blood with the probe. So we went through and answered this question over the last decade, and we're pretty confident that we have a very neurocompatible material, both in terms of the biocompatibility and the hemocompatibility. I'll show some examples of that. So silicon carbide materials, just to give you the big picture perspective, just like diamond and silicon, it's a tetrahedrally bonded covalent semiconductor. In the case of diamond, you would see all carbon atoms. In the case of silicon, all silicon atoms. Here we see silicon and carbon interleaving in different atomic levels. It's been around since the 19th century, been used in cutting and abrasive materials, again, since the 19th century. What's interesting about silicon carbide compared to diamond and silicon is that it forms in single crystalline form in more than 200 different crystal orientations. These have actually quite an interesting technological ramification. The 4H material is a hexagonal polytype, as we call it, used in power electronics. 6H is a great support for LED lighting, used by Cree and other companies. And the cubic form can be grown on silicon wafers, which we'll get into in a moment. So the very first blue LED in 1907 was realized using silicon carbide. So it's been around for a very long time, but it was difficult to manufacture. And that's why it took about 100 years for it to hit the market. All the silicon electronics that are used for computers and for switching power and so on have been realized in silicon carbide. And my lovely wife wears on her finger a moissanite gem, which actually is 5 times as brilliant as a diamond, at about 1/3 of the cost. So it's really nice that silicon carbide covers the full spectrum from bling bling to wearing down materials for cutting and so on electronics. So quite useful. So how do we get this material? How do we achieve what we need to make these devices? Well, we start with silicon wafers, the same beginning point for the silicon microelectronics industry. We load it into a reactor. We cook our wafer with the right gases, and then out comes the film. We can grow at about 5 to 10 micrometers an hour. Then when we do that, we get a very nice, this is an example of a 100 millimeter 4-inch wafer with a pretty uniform silicon carbide film on top. This cross you see here is a reflection from the ceiling tiles in the laboratory. And the color fringes are slight thickness variations due to the fluid flow. So we're able to then take, and from this 4-inch wafer, we can make thousands of Neuro probes, for example, using batch processing. So what are some of the other examples of silicon carbide biomedical devices? There are impedance sensors for myocardial monitoring for the heart. There are silicon carbide coated bone prosthetic devices, again, to reduce inflammation caused by metallic ion, let's say, corrosion in the body and shedding of ions into the tissue. There's a very nice application for cardiovascular heart stents where these are coated with silicon carbide to reduce biofouling and thus give longer life to the stent. And then the example close to our discussion today is shown here. It's a peripheral nerve electrode, which is one that would wrap around a peripheral nerve to allow us to both record and stimulate. And normally these are made from plastics like polyimide and so on. And in this case, it was coated with amorphous silicon carbide to improve its wearability and to reduce the uptake of water, for example. If a polymer gets wet, it normally absorbs water, it'll swell, eventually crack, and then the material begins to fall apart, which, as you can imagine, is not a good thing to have happening in vivo. So let me continue on to this part of the discussion. Some of the work that I was involved in is shown in the next slide, which involved microdialysis using porous silicon carbide. These are very nice non-fouling pores that can be used for microdialysis in the body. Getting into the nano area, very nice cubic silicon carbide quantum dots to use as fluorescent markers for in vitro cell biology. And what's nice about these compared to other optically sensitive markers is that there's no quenching. These can be ingested by cells and can fluoresce indefinitely, unlike other chemical markers that only have a certain period of time that they'll be active. You hit them with UV light, they fluoresce different colors. You can see where these are in the tissue. What got me involved in this, and I'll tell in a moment a short story about this, was when I saw this data. On the left image, you'll see bone cells, osteoblasts growing on porous silicon carbide. A very nice conformal, thick layer of bone growing on an inorganic material without the need for a protein interfacial layer like hydroxyapatite. Whereas the same bone cells exposed to traditional silicon are not adhering at all and not proliferating on the surface. And so for me, this was the genesis of my moving from silicon carbide electronic materials research into the biomedical area, was seeing this data. So in fact, let me just take a moment and talk about that. When I was younger, back in the day, in the 70s, I had a bone tumor in my lower left leg, and I had, was in high school at the time, probably a sophomore in high school, and had been taking chemistry class, and I went to the surgeon and asked him, how can we do this? Well, we're going to open up your leg, and we're going to take out the tumor, biopsy it to make sure it's not cancerous, make sure it's benign, and then we're going to open up your hip, and we're going to chisel out, quite literally chiseling out, a bone that we're going to use to fill the cavity. And I asked him, can't we just go with the needle, go grab a couple of bone cells, put it in a petri dish, and culture it? At that time, there was no way to grow bone outside the body. We literally had to take and harvest bone from our own bodies to do this kind of a thing. Well, now we can have scaffolds, or we can grow bone in the laboratory before we have the patient go to surgery. So you can imagine the reduced surgical time, the improved healing time, and my dream, and it's a little bit of a crazy dream, but I guess I can do that every now and then, right? is I had to go for periodic x-rays to make sure that there was good osseointegration of my hip bone with my leg bone, and so on. We could think about smart implants that can be engineered. We can do an exact form fit for whatever shape, size, dimensions we need for the bone, do that a priori before the surgery, and even embed sensors that will allow us to monitor in real time the osseointegration, the acceptance rather than rejection of the implant. So this is still my dream. It's what drives me to do this, and that's pretty much how I got on this path. So we'll have some time, I think, later to talk about that at the end of the discussion. So let's continue on here. Let's get into a little bit of the details. This shows a snapshot of some of the different in vitro cell cultures we did. For any biomedical device to be approved by the FDA for translation into a product, it must pass a regimen of testing, a battery of testing, in vitro, in vivo, and also chemical robustness, chemical wear. And so here we see PDOT, parylene C stiffened with aluminum oxide, cubic silicon carbide, and amorphous silicon carbide in the lower right-hand figure. And I know it's a bit of an eye chart, but the idea is that these fibroblast cells should be adherent to the surface. They should adhere, they should flatten, and they should proliferate and eventually cover the whole surface. And for the trained eye, which many of us are not trained in, what we see is nice triangular-looking cells in the lower left and the upper right image. This is what you're looking for. Of course, this is very qualitative. Then we will go and do some quantitative analysis comparing the number of live cells and the number of dead cells. And then we can assess whether or not these materials pass the ISO standard. It's ISO 10993. So I'll show you the histograms in a moment. So here we see the negative control that's normally used for an insulating material. And silicon carbide worked really well. Probably you're all familiar with graphene if you're in the nano area of research and education. So we, of course, were thinking about graphene as well. Is it biocompatible? Would it make a good conductor to replace metals, which we know shed particles and ions and are actually not terribly compatible with the body? And the answer is yes. We did a bunch of work on this about a decade ago and showed that real graphene, not graphene oxide, is in fact quite biocompatible. And graphene, of course, is a 2D material. If you roll it up into a tube, it's a carbon nanotube. If you roll it into a sphere, it's a buckyball. For those that I think everyone's probably familiar with that at this point. So in the first of 2 books on silicon carbide biotechnology that I put out there, we see a very nice in vitro cell culture study done with multiple stains. Blue is for the cell nucleus, red is for the actin mesh, and green are for the focal point adhesion. So we can see where the cells are actually attaching to the surface of the silicon carbide material. In this case, it's graphene. So these are human keratinocytes, very nicely adhering and proliferating on a graphene surface. So again, more proof that graphene is potentially good material to use for biomedical devices, which we know quite well. So going back to my earlier comment about going from the qualitative optical micrographs, fluorescent micrographs of cells on surfaces to summarizing the data in a more scientific way. Here we see in the upper left-hand graph biocompatibility, the upper right-hand graph hemocompatibility. Let's talk about biocompatibility first. We'd like to see the number of cells that are resisting or surviving on the surface be at least 70% of a control well, where there is no foreign material. And so this dotted line, dashed line, shows that level. Silicon does pass the test for a short period of time. After a few days, it also fails the test. I believe this data comes from a 72-hour experiment. But if we run into 7 days of cell culture, silicon begins to really fail the test. Oxide, silicon dioxide, is shown here in red, is the normal way that we protect silicon from the environment. We use it in microelectronics, both to passivate silicon and also as a gate dielectric. Well, it turns out that silicon dioxide is not really compatible with the body, and we've seen this in several studies that we've done. So the standard solution in the silicon world of just coating it with glass doesn't work. Cubic silicon carbide, or 3C silicon carbide, shown in green, does extremely well with almost 100% cell viability. And the purple bar is the amorphous material, which also does well. Not quite as well as the cubic single crystalline material did, which was surprising to us, but still clearly well above the threshold for passing the test. On the right-hand image, we see the hemocompatibility results, and what we're looking for here is a very short, very small histogram. We want to see where the y-axis are 1,000 platelets per square millimeter. And after 15 minutes of exposing the surface of the material to platelets and platelet-rich plasma, we want to see a very small number of platelets that are adhering to the surface and that they're circular in shape. So what we see here is that cubic silicon carbide does extremely well. Again, amorphous silicon carbide does well, but oxide and silicon clearly do not. So the bottom line here for all of this, after spending a number of years working in the cell biology area, is that only cubic silicon carbide passed the ISO 10993 test, both for chemical stability and for biocompatibility. So clearly this motivates us to move from the materials realm into the device realm, what we're doing. So I see there are maybe some questions.
There is, Steve. It's Mike.
Yes.
I'll do one first, and then I'll ask Ozgur to chime in as well. But one of the questions just came up, and I had the same one myself. A lot of folks online, I recognize them. They're in the MEMS area, and they're often dealing with microfluidics and things like that. How has silicon carbide been used in those applications? Are there adherence problems? Is there compatibility in that MEMS microfluidic sense?
That's a very good question, Mike, and everybody else. It's pretty much the same as what you get in the silicon world. So if you do the classic, if you etch a channel and you put PDMS over the top, for example, it works as well with silicon carbide as it does with silicon. Only now we have this very nice compatible material for the body. One of the other questions I see here in the chat window has to do with ceramics being brittle. Well, it turns out that silicon carbide is surprisingly flexible for a semiconductor. It has a Young's modulus that is 3 times, I guess, superior to silicon. And I'm going to show later. I didn't have time to show the video today, but I have a video that shows Neuro probes bending 90 degrees and snapping back and not breaking. It's quite phenomenal. So I'll show just a snapshot of that later.
Interesting. Let me invite our colleague Ozgur to come on and unmute the microphone. Ozgur, do you have a comment or a question?
Oh, actually, I was quite surprised that they were able to distinguish the silicon and the silicon dioxide, since we have the native oxide growth happening so quickly. What would you say about that?
That's a very good question, Ozgur. So we went through a lot of trouble to make sure that we reduce the oxide on the surface using HF, and then quickly immersed these samples into ethanol to prevent oxidation, and then straight to cell culture. So there may be a very thin native oxide, even for those silicon samples. But we went through a lot of trouble. Since we understand microelectronics, trying to control that, as you know, is difficult. So I would imagine there's a few monolayers of oxide on the silicon surface. In the case of silicon carbide, I guess the good news is that the native oxide is also silicon dioxide, but it grows very slowly. Mm-hmm. So we went through the same trouble. The last chemical cleaning step before immersing it in cell culture was to use buffered HF.
Right.
And again, directly, we literally rinse it in DI, immerse it in ethanol, and then go off to the biolab to do our cell culture.
Yeah, so questions were coming actually related to the deposition of silicon carbide. What could we say about the growth, the deposition of the silicon carbide?
That's fantastic. Yes, so we use silane as our silicon precursor. Also, we can use trichlorosilane. There are other silicon-containing gases one can use as a silicon source. This is grown in chemical vapor deposition, at relatively high temperatures. In the case of 3C, just below the melting point of silicon. And the carbon source can be your normal suspects. We typically use propane. We also use ethylene. so there's different ways to provide carbon, and of course, getting the right mass balance. We do that with mass flow controllers and everything. And anyone who wants to hear more about that, there's a very rich literature on how to grow silicon carbide. We've had this around for a long time. To answer the question about electrical conductivity, we can do the same thing we can do in silicon. We can grow N plus material, N plus dope material, P plus dope material. Unlike diamond, we don't have a problem growing both polarities in the up to the 10 to the 19th range. Pretty much everything that we do in silicon, we can do in silicon carbide. The difference being that it's a higher temperature growth process. But the most important thing for the biomedical device area is that wet chemical etches do nothing to affect any change in the surface of silicon carbide, which is why it seems to work so well in the body. Whereas you can etch silicon, gallium nitride, and so on with wet chemical etchants, you cannot really do that in silicon carbide. The only wet chemical etch that works is molten KOH at, I think, 400 degrees Celsius. So pretty much molten salts begin to pit the surface of the material where there are dislocations. So it's extremely robust and impervious to wet chemical etch.
Interesting. Steve, I'm going to interrupt this mic. I think for the interest of time, we'll save our questions for the next break, but I'm now going to contact my broker and invest in silicon carbide futures. That's my
Sounds
action.
good to me. Let me know how that turns out.
All right. Go ahead then.
Thank you. Okay. Let's continue on now. So let's talk a little bit about the devices. It's so important for us to translate these pretty remarkable materials properties into working devices, and we've done that at the prototype level at the university. So one thing that we've done is to take a very simple, we can also make semi-insulating silicon carbide. You can buy this on the market, and these are extremely insulating materials, and then we can put things like metals on top to make patch, microstrip patch antennas. We did this for a glucose sensor operating nominally at 10 gigahertz. And here we see in this plot, we would take this, in practice, we would take this device and plant it in the fatty layer near the epidermis where we can see blood vessels. And what happens is the glucose actually changes the permittivity, electrical permittivity of the blood. That's the mechanism. And so we're able to sense the glucose level directly by a frequency shift in the resonant frequency of the antenna. And so in this left-hand plot, we see the following. Let me walk you through this. On the horizontal axis is the concentration of glucose in milligrams per deciliter. On the vertical axis is the frequency of the resonant frequency of the antenna. And we have two curves. One is actual pig blood, where we took blood harvested from a female farm pig and added glucose to it, and then looked at the frequency shift. And one is where we used the blood mimicking solution. And in both cases, we saw a quite linear change in frequency through the glucose level that we care about, which is more or less the blue window shown here. Green is where a healthy patient who doesn't suffer from, let's say, type 1 diabetes or type 2 diabetes would have their glucose level. And then light blue is where we have to worry about the full range of glucose typically for people who have this type of challenge. And so you see in all these cases that we have quite a nice linear change in frequency versus glucose concentration, which is the kind of thing you want to have in a sensor. So we did that quite a while ago, and that work has been just put up for patents. We're waiting to see how that goes. And then the next thing that I had a student doing, she's now at Intel in Oregon, was to, her father passed away when she was young from a heart attack, so she wanted to work on some means to measure the onset of a heart attack as quickly as possible to help save lives, which is, of course, is a great thing. So one way to do this would be more of a ChemFET, where we would replace the gate on a MOSFET with some antibodies that would bind to some, for example, blood marker in the blood that would change electrical conditions on the gate, and we could sense this very sensitively, which is one way that these chemical sensors are made. Or we can use what's known as an impedance-based sensor, where we can do the same thing. You see here on the surface, antibodies are bound to the surface of a comb electrode structure, and then when, in this case, myoglobin binds to the antibody, it changes the charge present on the surface, and we can sense this change in charge. So Alexandra, now Dr. Oliveros, did a nice job here And here we see an example of what the sensor looks like. It's quite small. So she spent a lot of time functionalizing the surface and doing all the biochemistry that many of you in the audience today know more about than I do. And what was nice about this, as shown here in this data, is that she looked at the silicon carbide surface functionalized with APTES. BSA is bovine serum albuminum, I forget how to pronounce that. So it's the bio stuff. And we can look at an anti-myoglobin situation or an anti-hemoglobin. So in this case, we needed to distinguish between myoglobin and hemoglobin because, of course, hemoglobin is always in the blood. And what she saw is that we had a pretty nice positive detection of myoglobin with a very low false detection of myoglobin when we were looking for hemoglobin, when the antibody was to bind to hemoglobin. So it was quite nice work. We published this some time ago. Again, an example of a type of biomedical sensor we can make using silicon carbide. And by the way, that's very similar to what's done in silicon. There's no big difference here other than our sensor would be longer lived in the body because of the biocompatibility. So along the same sensor line, I've had a long-term collaboration with the group in Grenoble, France. In fact, I'm going there in a couple of weeks to sit in on a student's dissertation. I'm on the jury. And they're using silicon carbide coated nanowires to look at DNA, which is quite interesting. And so the idea is that they etch a very small nano dimension nanowire, coat it with silicon carbide, metallize the source and the drain, put on probe DNA particles, and they can then measure DNA when it attaches. So it's a very nice room temperature electronic way to measure DNA, which is different than a lot of the assays that are done now. So what they discovered was that just by having silicon nanowires was not stable over long periods of time, and the signal was not reproducible, which was not a good thing. But then when they coated it or used silicon carbide as nanowires, they were able to get a very nice, stable, reproducible result. So this is the basis of the student's dissertation who he's defending this month, February. So let's move on. Oh, okay, some more about that. Of course, we can do all of the usual nanoscale device fabrication, source and drain with the nanowire between the two metals, and make arrays of these things and so on. So it's quite nice. The nanowires are grown by a group in Parma at the CNR that I collaborate with, which is also quite nice. And I'm using similar technology for a cancer project. I'll talk about that later in the talk. So it's a very interesting application of silicon carbide nanotechnology for this type of thing. So let's talk about brain-machine interfaces and the related technologies and how we got to the point where we believe this is a good solution to this challenge. So as we've discussed before, cubic silicon carbide has many useful properties, and it's a very nice material for neural interfaces for some very important reasons. It's 3 times as hard as silicon, but it has 3 times the flexibility. So if you're familiar with NeuroNexus and other silicon planar electrodes, they have a breakage problem. We can make these more robust. More importantly, we can make them thinner, which actually results in less surgical trauma and less rejection of the neuroprobes by the brain, which is obviously very important. We have our very good bio and hemocompatibility data. We're talking about materials that are as good as plastics, such as polyimide and parylene C. And what we like about this very much is that silicon carbide can be micromachined. You can make MEMS and NEMS just as you do in silicon. So we can do all the same things that we do in the silicon world to micromachine a device for various applications like Neuro. So here we see a black rock, a 2D array of silicon probes that are coated with different materials. They've also been coated with amorphous silicon carbide. But this is the technology we're talking about. This black rock array is the only array approved by the FDA in the United States for use in humans. It's been used to really help a lot of people out. So we're looking to basically make a more robust, more neurocompatible version of this device right here using silicon carbide. So the first thing that we did, Dr. Chris Fruin, one of my former students who's now at NeuroNexus, in fact, he started out doing cell assays comparing cubic silicon carbide with nanocrystalline diamond, NCD, and polycrystalline diamond, also polyimide, in this case, Kapton tape. And so we're looking at two cell modeling lines, H4s and PC12s, and the green bars, the most important one, those are primary wild-type mouse cortical neurons. And what you'll see immediately is the following, that once again, silicon carbide, the cubic form, outperforms silicon, but it also outperforms diamond. And its performance is almost on par with Kapton, which is quite remarkable. So again, this was further proof that this material may be very suitable for BMI applications. So how do we micromachine them? The same methods that we use for silicon, deep reactive ion etching, and so on. And so I see there's a question about lithography challenges for the DNA sensors. I'll talk about that later. But here we see an example of the top image, a Neuronexus functional probe, I believe the 16 electrode probe. And here we see just our physical shank. It's not a functional device with a nickel mask that we use to deep through. So what's interesting, again, here's some data that was taken using nano indentation. So you'll see here that if I do this right, sorry, I'm going to go back, that we have, again, the values measured for hardness, Young's Lessig modulus, and the fracture toughness. Now, the fracture toughness is really important. And we see here in the last column that we have a very good fracture toughness for silicon carbide compared to silicon. The top row is bulk silicon. The next two rows are thin white, about 1 micron thin films of silicon carbide on silicon. So again, looking in this window here at the bottom, the main advantage is we can make thinner probes, we can be as durable, and we can implant our probes in the same way that Michigan interfaces would be implanted, but we can do it with a much thinner cross-section, which reduces, again, the trauma and increases the probability that our device will continue to work in the for a longer period. So how do we make these things? This is a little bit of an eye chart, but we start out by growing, again, as I showed before, silicon carbide on silicon. We do the usual photolithographic steps and etching, handle wafers, and so on. And finally, we come down to the lower right here, and we have a freestanding probe, which we can pick up with tweezers. And getting back to the flexibility issue, my postdoc at the time came to me with this image and said, wow, this is his index finger, I believe, the glove. He took the tweezers and he kept bending this back and forth like a piece of cooked spaghetti, and it just kept bending and didn't break, which is pretty amazing. So again, it's hard material, but it's also flexible. It's quite nice. So what we did for our in vivo studies, we prepared two sets of probes. One was for the left hemisphere of the mouse, a mouse brain. The other one was for the right hemisphere. One side were two triangular, very damaging, very sharp silicon probes. The other side were two triangular, very damaging, very sharp silicon carbide probes, and we use that to do in vivo studies, which I'll discuss in a moment. So again, we can make MEAs. Here we see a 64-channel MEA that's packaged. We can make, at the bottom here, you see these Neuro probes that are using dental adhesive epoxy to these plastic headers that can be used to put into rats or mouse brains. And we've done surgeries with 6-micron thick probes in rat brain, and it was possible to actually get them into the brain of the rat without breaking. It's quite impressive. So, sorry, microelectrode array. So MEAs are microelectrode arrays. You can make an MEA as shown in the upper image that's both planar for in vitro studies, and also you can realize these multiple electrodes, microscale, on these sharp needles here as well. So thank you for asking me that question, so I don't use terminology that everyone's not familiar with. So Johnny, and as I always like to say, here's Johnny. Johnny is a very interesting person. He lives close by to Tampa in a place called Newport Richey, and he was kind enough to come by and visit with some pre-college students who came to the lab last summer. He has a very advanced arm called the MPL, developed by Applied Physics Laboratories in Columbia, Maryland. He's one of the only people on the planet that actually has a robotic arm that's also integrated to his bone. So you see here a stainless steel, really a ball and socket type of joint. He can take this off at this silver area at the end of his arm stump. These black bands are sensors, Wi-Fi, and Bluetooth. So at the moment, he's able to control this arm. He's actually learning to play piano, which is amazing. And the funny part about that is he never played piano before. He had both of his biological hands, but now he's learning to play piano with his left robotic hand and his right biological hand. We want to get rid of those sensor bands. We want to have the interface to his arm directly through the robotic mechanical support that's shown here, so that we can directly intercept those neural signals and go straight to the robotic arm. And that would greatly improve the functionality and reliability of what he's doing here. Because again, every time he puts these bands on, they're not exactly aligned over the same muscle and nerve endings as they are when he puts them on. He has to take these off to wash and so on. So if these black bands were not there and they were integrated inside of his arm, he literally could shower and everything with this device without having any challenges. So how are we planning on doing this? We plan on doing this as shown here. These are devices that we're actually going to finish fabricating next week up in Michigan, if I can get there with the polar vortex. But these are 5 millimeter long probes with 16 electrodes meant to fit into an Omnetics connector. So the idea is that we would not even need to solder any connections to this, and we can then use this to do our animal studies. That's our plan. And then from there we'll get recordings from the mouse or the rat, and then we'll be off to the races here with our technology. I'll talk about that a little bit more later. Well, I'll talk about it now. So an all silicon carbide intracortical neural interface, or INI, is shown here. The left image is the mask for a planar device. These are single-ended electrodes on top. You'll see a rectangular metal pad that we use for probing or for wire bonding. The top end, these circles, are actually the neural interface that would be exposed to the brain. In this case, electrochemical solution. On the right are cyclical voltammetry measurements that have been done. The most important reason why I show this data is it's comparing gold, platinum, titanium nitride, and sputtered iridium oxide interface. What we're looking for is a little bit of hysteresis effect. So as we increase the potential to, let's say, a volt or 0.8 of a volt, and we go back to minus 6 or 7/10 of a volt, we'd like to see a nice area under the curve. That area relates to the charge capacity of the electrode. We like to have a high charge capacity, which means we're getting efficient transfer of charge from the brain, both from the probe to the brain and then from the brain back to the probe. So what's nice about this first trial, these were really our first devices made using hexagonal silicon carbide 4H, that we were already having superior performance to a platinum neural interface and beginning to come close, if you look at this green curve, to titanium nitride, which is quite nice. So if we continue on a little bit about what we've been doing here, we're trying to improve the charge capacity also in Grenoble by doing nano texturing. So we're nano patterning using nanolithography, the surface, and then we're creating these pillars to increase the charge capacity even further. So let's talk a little bit more about the in vivo performance, and then we'll get to the end of our talk. So here we see some of the glucose sensing antennas. We then coated them with both oxide. We put them in bare into the muscle of a pig subcutaneously. We coated them with oxide. We used polyethylene glycol as a protein inhibitor, and then we used amorphous silicon carbide on oxide to make this more robust. And the data that I'm going to show next is from 1 month in the pig. Here we see a tissue block where there was no device implanted. Looks very nice. And then if we compare that with these 7 micrographs, we'll see that even the titanium and gold are FDA approved, but look what happens to the tissue. There's definitely a response of the body to even these FDA rated metals. That's an important point. Silicon was simply put a disaster, silicon dioxide as well, but all of the forms that had silicon carbide performed extremely well. If you look, for example, at the lower left image of the all silicon carbide implant, you can't see any difference between that and the no implant tissue block to the right. And in fact, silicon, here's what happened in 1 month. You see this white plastic looking thing. This is a fibrous encapsulation of the actual silicon chip. Pretty amazing how quickly that thing got encapsulated and walled off by the body. So looking at the brain, those double triangle probes I showed before, here are the results. The left column is silicon. silicon probes, the yellow rectangle shows roughly the dimension of the probe when it went into the brain. The black area is, yes, you got it, that's neural death. That's where quite literally the tissue has died. And if we compare that with cubic silicon carbide on the right, you'll see that it was very difficult. This is all tissue histology, for those of you familiar with that, with multicolored staining. Here we see where it was really hard to even know where the implant was in the top image. The bottom image, a piece of the silicon carbide probe remained intact. And cubic silicon carbide fluoresces in the green. So what you're seeing there, it was very nice actually, quite fortuitous. We're able to actually see neurons in blue intimately connected to the probe after 1 month in the mouse's brain. Quite exciting stuff. So again, the challenge is now to translate this materials result to a device result. So that's shown here. Let me go a little bit faster. I was on a project, Science Without Borders in Brazil, at USP in San Carlos, Brazil, and for lack of a better thing to do, I gave these probes to students working in the lab with rats. And here we see on the left-hand image silicon carbide probes, and the right-hand image we see these commercial so-called MRI-compatible probes. And what you're seeing in the actual MRI scan is the lack of any image artifacts. We don't see white. Let me see if I can do this here. Show this. So we don't see this white image here on the silicon carbide side. We just see a lack of MRI signal from the implant, which is quite nice. So this made us think that, well, we may also have an MRI-compatible probe. And so we're currently working on that as well with a current PhD student. And here are some simulation results in ANSYS. Very quickly, we see, that was, by the way, 2 Tesla magnetic field. This is now 7 Tesla. And the upper left image shows the cubic silicon carbide without this red dot. We're looking at specific absorption in the tissue, which would result in a temperature rise, which would actually cook the tissue and kill the tissue, whereas iridium lights up like a Christmas tree, as shown here. The only material that passed the FDA limit for SAR was our cubic silicon carbide, which is quite nice. So we're continuing to work in this way, and we're currently getting ready to do some 7 Tesla in vitro experiments at the Moffitt Cancer Center at USF. So now that we went through all of that, and I'm glad to see that some of the comments here are quite pleased with these results. Thank you very much. Let's talk a little bit about the educational opportunities, and I want to give you some examples of more cool stuff that I'm involved with that really motivates in my mind how we need to educate the next generation workforce. So we're looking at using silicon carbide nanostructures for deep tissue cancer. This is an NIH R21 project that we started last year. We're trying to do X-ray excited optical luminescence. And so this cartoon, which is quite hard to see, it's a little bit fuzzy, but the idea is that we would take a very nice working conjugate. It's called IR700 with an antibody. The antibody only binds to the cancer cell membrane, and then the IR700 binds to the antibody. When you hit that complex with infrared light, it disrupts the membrane and kills only the cancer cell. It's extremely specific. Unlike chemo and radiation therapy that kills all the tissue that it's exposed to, this only kills the cancer cells. They're having, at the NIH, at the National Cancer Institute, amazing results in clinical trials, but only for surface tumors, untreatable surface neck and head tumors. What about deep tissue cancers such as liver, pancreas, and so on? So the idea is that we would introduce this antibody IR700 complex in deep tissue and then put close by, in close proximity, silicon carbide nanowires or nanoparticles, hit it with X-rays, and then these X-rays would fluoresce in the infrared and then do the job of killing the cancer cells. That's what this project is all about. So again, a great example of nanotechnology. And here we see the absorption of basically the radiation as a function of wavelength. We're trying to get near 690 to 700 nanometers, as shown here. But this shows that it's also possible to shift the emission from nanoparticles in this case. These are about 6 to 10 nanometers in diameter. We're able to shift their luminescence from the green to the orange simply by controlling the surface chemistry of the particles. In terms of nanowires, these are what are called core shell nanowires. They're coated with the silica layer, and we can also control to a certain extent, and we're working on this right now. We can control the luminescence of these nanowires. We hit them with X-rays. So it's quite nice results. More work involving nano. One of my former students, Dr. Camilla Coletti, is in Pisa, working at the IIT. So we're working with her on graphene, trying to make these neural electrodes with graphene metallic layers. So that's a very nice work, and she's also obviously interested in a lot of things, including cancer treatment. So that involves more friends in Europe. So let's talk a little bit more now that I've gone through all of these different things. I've covered a tremendous amount of technology space. And I guess I'd just like to say that clearly, if we're going to prepare the next generation of manufacturing folks, of technicians, of obviously engineers and scientists, we're extremely cross-disciplinary to do that. We're talking about not just the physical realm, also software, cyber. We need to be able to handle all of these things if we want to bring these products to market. So it's materials, it's science, engineering, it's software, cyber, and so on. So it's really exciting but quite challenging to cover such a broad swath of the known technological space. So, how are we going to do this? Well, I believe we must find a way to do this, and this is why I'm happy to present this webinar to all of you, because I'm sure you're much better educators than I am. It's not going to be easy, but we need to provide sufficient depth in a given field to make a difference. So we don't want to be an ocean of knowledge a centimeter deep. We need to have some depth in different areas to be able to really make a difference. But then we need to have enough breadth. The student must understand how their part of the puzzle fits, right? And that's really hard to do, obviously. Certainly at the community college level, we're teaching them different areas to go deep in, and then we can hope that we can broaden their knowledge at some point. But being able to help the student visualize where we're going with the details is really important, and as we all know, that tends to be challenging. They have to work in diverse teams, and that means people from different cultures, different languages, different points of view. In my case, in particular, just having PhDs working with MDs is hard because we think of things in different ways. I always remark to my colleagues and my students that when I talk to a medical doctor, what they think is hard for engineers is easy. We're like, oh, that's easy, we can do that. And then the stuff that they think is hard, or that we think is hard, they're like, oh, no, we can do that. And so I find it interesting that just by having a different perspective, you're able to come together and overcome challenges that are in these type of research and development projects. So one other thing that's really important is that it's not just technical stuff. We got to be savvy in terms of marketing and sales and how you construct and how you make money with these things, right? So we all know that making a better mousetrap is part of the objective, but if nobody cares, or if we can't do it in a cost-effective way, it's not going to go anywhere. So we need to build into the students as early on that they need to keep an eye on the economics of what we do. Having the gold-plated, extremely expensive solution doesn't really go very far, right, in a practical sense. So I believe that to educate the next generation workforce, each area that they're working in needs to have value, obviously. They need to be able to add value and overcome challenges, but they need to also do it in a way when you put it all together, you're getting to your desired outcome. So I showed you examples of technology that covers the gamut of the things that we work in: chemistry, biochemistry, physics, electrical engineering, chemical engineering, mechanical engineering. We cover all these things. So we got to have depth somewhere. Each one of us, as part of the team, needs to be responsible for one key area of the thing. And that's, as we know, that's easy to do. One area we're good at, but being able to interact with others in a way that works as the ensemble. It's like the conductor getting the orchestra to play. Everybody has to be able to play in tune, right? So how do we do this? Is it a top-down thing? Is it a bottom-up thing? Everyone learns differently. So I think that I find some students want to know the theory before they see the application. Others want to see the application before the theory. I do think that independent of all of that, trying to impress upon them the importance of what they're doing and having them see where what they're learning leads to useful things. I do think that that's pretty a pretty common thread for most students. They want to know that you know, sitting through. I just had a student come to my office the other day. She wants to change from biomedical engineering to biochemistry because she's not enjoying her Calculus 2 class. I'm like, really? So what's the challenge there? Oh, well, the professor's hard to understand, and I'm a little bit confused. And you say, wow, you know, you're going to change majors because of one professor in one class? That's a scary prospect, right? Hands-on projects, thank you, Matthias, is extremely important. I teach a course called Bioelectronics every spring semester. The students pretty much do it's BME students, biomedical engineering students, and EEs together. We've even had medical doctors in the course. They work together on building something, to design and build and test some type of bioelectronics gadget. It's quite impressive what they come up with. So yeah, hands-on projects definitely help because it forces them to work with colleagues that are involved in other details they don't know much about. So it's a very good comment. Thank you. So I guess I want to just wrap up here with the final thought. Obviously, we have this collage thing. Is this a repeat of what I just talked about? Yes. So I want to thank a lot of people from all over the world. I've really been blessed to be able to work with some amazing people all over the planet, which is wonderful. My group, this is actually an old photo of the group, and I can't help but put a shameless plug in for my 2 books on silicon carbide biotechnology. If you sweet talk me and send me a nice email, I'll send you the ebook. Just don't tell the publisher, okay? But these are out there, and you can get them on Amazon if you're interested. And it's really a great way to get a quickly spun up on what we're doing here. And if anyone's interested in collaborating or has some ideas on how to help me move things forward, I love to work with great people and would welcome that type of interaction, absolutely. And so I leave you with the following thought. I'll read this for you. It says here, the computer says I need to upgrade my brain to be compatible with its new software. So I'm joking about this. This is from 2000, but I realize now that we're getting close to the point where this may become more of a reality than not. And some of my colleagues say to me, why do you care about cybersecurity? I'm like, well, we have a lot of devices now, implantable devices. Pacemakers are a good example that are Wi-Fi enabled. And we got to make sure that these cannot be hacked to either intentionally or unintentionally hurt people. So I'd like to thank you all for your kind attention, and I think we have time for questions. Is that right, Mike?
Yes, thanks, Steve. I appreciate the comments, appreciate the cartoon. Don't mind the shameless plug for the Amazon books, so thank you for that. We are slightly over time, so I'll let people know that if they have to leave for time constraints, please go ahead. But we'll take a few minutes and answer a couple of questions, Steve. One is, you were talking about the education challenges, and Matt made several comments. One was about T-shaped students, and I think that's very consistent with what you're saying. And that term, have you heard it? It's students that have a broad knowledge, that's the top of the T, but also a narrow, much deeper knowledge in certain areas. And I think that can really work. I think you were sort of saying that.
That's exactly right. I hadn't thought about that. I hadn't named it, but that's exactly right. Thank you, Matthias, for putting a name to the idea. So
let's follow up on another of his questions. Any litho challenges? You're not really talking about small features here, are you?
For the neural interfaces, they're more or less micro scale, but for the nanotexturing, yeah, we're talking about 50 nanometer diameter little cylinders, silicon carbide. We're trying to etch them very deep. For the DNA sensors, yeah, those are very, very narrow nanowires. The nanoparticles for the cancer, yeah, they're 8 to 10 nanometers, right? So we're talking about nanoscale. Also for nanoparticles, also the nanowires are typically 50 to 60 microns in diameter. But there's always one dimension, rather big,
yeah, right?
So that's. I hope that answers the question, Mike, as far as this goes.
Sure, it does. It does. The one other thing that came up in one of the questions was you mentioned biocompatibility. Is there any toxic issues? I mean, sometimes I can't imagine these carbide things breaking into small particles, but you know, there's a lot of awareness about small nanotype particles. Any issues related to small particle toxicity that you might have come across? That was one of the questions.
That's a very good question. We've never come across that because, again, we have evidence that silicon carbide nanoparticles are also highly biocompatible. But again, at the nanoscale, those are tough challenges. The fact that
Yeah.
cubic silicon carbide nanoparticles were ingested into cells and shown to fluoresce is quite encouraging. So you can imagine if these cells had been poisoned by these nanoparticles, they would be dead, right? There would not have been a cell body left. So they still, they lived and they went through their life cycle without any problem. So, but yes, that would have to be more exhaustively studied. And in fact, isn't that one of the challenges of nanotechnology in general? Is what do these things do in the body? Did they get flushed out? Did they accumulate? These are very important things to understand, right?
Cool. I'll make one comment of my own. I learned a bunch of things today, but it was, I think, the second time I've heard that term, electroceutical. I thought it was a very interesting use of the term.
Yes. Well, so the idea is to try to get away from drugs and try to affect changes in physiological functionality using electricity, basically. And so one of my colleagues, Dr. Hoff, is using, for example, plasmas to electroporate cells that he can then introduce drugs into the cell, porates the membrane, the drug goes in, the membrane reconstitutes itself, then they inject these things into tumors. So what you have, in a way, is a designer chemotherapy drug, where instead of a broad-based treatment for the whole body through an IV, in the hand or in the collarbone area, you're talking about directly injecting this into the tumor bed, greatly reducing the toxicity and greatly increasing the effectiveness by having targeted delivery. So I'm not sure I answered your question, but that's the kind of thing that we can do using electroporation. So that's, in a way, a merger of drugs with using modulation techniques. But there was a conference I went to last year, of all places in Las Vegas. And by the way, if anyone's ever been to a conference with medical doctors, if you get a chance to go. I was amazed. They had a closing reception, and they had cognac. And they said, well, can I get a glass of cognac? They're like, which one? We have 3 different types. I'm like, can I try? They're like, sure, you can have one of each. You can have as much. This is great, as opposed to our engineering conferences where you got to go to a vending machine and get candy bars, right? Or Cokes or whatever. But at this meeting were pain remediation doctors who refused to prescribe opioids, no Vicodin, no oxycodone, using electrostimulation to treat headaches. I have a friend of mine, his wife went through the usual medical regimen for back pain, severe back pain. Only paddle electrodes implanted on her spine have given her any relief at all. So we're talking about that, for those situations where we can avoid drugs and we can affect real changes to the body's functionality, we can do it with electrical means. That's a great way to do it. So electroceuticals are viewed as this large class of treatment modalities where we do just that. So I hope I answered that question.
Sure. It did. Steve, that's going to wrap up our question period today. I'm going to make a couple of announcements. I'll talk about the next webinar. I'll ask people to participate in our survey. But first, let me thank you for all of the prep work that you did in getting this together. It was just fascinating. Great comments from the chat window. I think people really took away a lot today. So thank you again for your time and effort on this.
Thank you very much, Mike, for inviting me and all your organization, you and Bob. And you guys have been great. Thank you.
Okay, good. So let's go ahead, folks. Please, here's my announcement. Join us for our next webinar, February 28th, 2019 at 1 p.m. Eastern. This one's going to address the strategies that we all can use to build enrollments in our nanotechnology and STEM programs. And I know, and we all know across the country, that's always a challenge for us. How do you do it, whether you're at high school, whether you're in community college, technical colleges, universities? How do you build those enrollments, and what does a nanotechnology program mean? A lot of different variations. 3 expert presenters who have faced the challenges themselves on that. So please sign up by going to the website, the Nano4Me website, the NCI Southwest website, and listen to our emails. We'll promote this thing coming up. So again, as we wrap up for today, I think most of you know what's going to happen. I'm going to launch this survey. It'll open in a new window, just 4 questions, and just go ahead and do that. So that officially ends our webinar. I'm going to stop the recording today and launch the survey. Thanks, everybody, for joining. Goodbye.